Tiernan Barber, and this is Bomberman, defining and defeating hardware kicking time bombs at design time. So, this paper is focused on a very specific type of hardware Trojan. It's implemented during the front-end design of an integrated circuit. All of these stages have possible attack points, but front-end specifically has a design time attack point. Well, how could this happen? Like if we're designing hardware, why would the RTL design be a vector of attack? Don't we make that ourselves? Well, usually that's true, but now designs like fabrication are also being outsourced to smaller subcontractors. Design studios don't often have the time or the resources to design every little part of their whole integrated circuit, and so we'll outsource parts of it to other manufacturers or other design studios. So Trojans, this is an example of a side channel Trojan that's already been activated. The payload has been delivered, and it is broadcasting without the core of the IC knowing the AES security key, and the attacker can pick up on the signal and reverse engineer it, which is why it's so important to address these things before they make it into hardware. There are already some existing approaches, but these general-purpose hardware malware checks often fail to find very specific, specialized hardware attacks. So this paper is focused specifically on ticking time bomb Trojans, how to detect all forms of them. It provides a toolkit to identify them for further review. The point of this tool is not necessarily to be 100% accurate, but to encourage hackers to use larger, more complex designs to evade this test suite in order to go undetected, and then those larger circuits, which require more complex design, will be more likely to be detected by the existing general-purpose scans for suspicious hardware. So a ticking time bomb Trojan includes a sequence which never repeats a value that increments upon an event signal. So it's defined by a counter. The paper calls these state-saving components. So the time bomb includes a state-saving component, a counter, which could be a flip-flop, a register, or even a latch, an increment value, how much the counter increments by every time the event happens, which could be the clock edge, it could be a page fault, it could be something more random, so it's a little bit harder to detect. Amongst the types of hardware Trojans, we're already talking about dormant ones that are harder to detect during testing because they're not immediately activated. There are cheat code based ones or data based hardware Trojans which activated upon a certain combination of signals, but these often require physical interaction or access to a device, whereas time-based Trojans can just activate once the device is deployed, which makes them more lucrative to attackers. Amongst these, there are individual systems, so they call these coalesced, where the one state-saving component is the whole system, and then the differences here are how often the incrementation happens and by what increment the counter is increased, and these determine the uniformity and the periodicity of the coalesced time bomb Trojan. Distributed ones are just multiple coalesced Trojans together, but they all have to activate at the same time in order for the event, the payload to be delivered. The three of those, when they activate together, would activate the event. When they activate individually, they don't, which makes them harder to detect as suspicious. So there are some examples given of how the clock and the page fault can be used for the time of the increment, and there's also examples in the paper on how to use the program counter itself to sort of randomize the incrementation. There's an example of how to implement homogeneous counter using two uniform periodic state-saving components, and there's one that uses two kinds which increment at different intervals based on the clock or page fault, and increment uniformly with one or use the program counter. So these are some existing general purpose approaches, which all three of these listed are basically just a scan for rare circuitry or things that isn't really activated during testing. Why is that not being activated during testing, since a test bench is supposed to iterate over all of the possible uses of hardware? So A counter that doesn't go used, or a signal that is seemingly benign but never changed, can be a red flag for further investigation. So if we have these specialized attacks that fly under the radar of general purpose approaches, then the solution is clearly to develop a specialized hardware check. So they call this Bomberman, which looks for state-saving components that don't repeat a value without the whole system resetting, and doesn't enumerate all possible values without activating. This can be a little bit difficult because of the distributed nature of some of these state-saving components, which use multiple counters to obscure the system. But Bomberman manages to detect these as well. It has a two-step process which identifies components that are counters and classifies them as suspicious or not. Something important to note is that Bomberman immediately assumes at the beginning that all state-saving components are suspicious. It can be very good for the system to have false positives but no false negatives. It's not going to say this counter is benign when it isn't. It's going to say something is suspicious. It's always going to default that a counter is suspicious and needs to be further investigated. So, step one is pretty straightforward. It looks for any collection of flip-flops or latches or registers. It looks through the Icarus Verilog front end and creates a data flow graph with a custom C++ API to see the bit level signal dependency, which highlights state-saving signals that are gated and intermediate signals from combinational logic. It can even work with procedural assignment expressions like the one you see on the left there, because it uses template matching like a lot of HDL compilers already do. And then it uses a Python script to pour through the nodes of this graph. And every node that's an output of a gated flip-flop is considered a coalesced state-saving component. Then a graph of these, a search is performed on these nodes to piece together any distributed components using depth first search. In step two, we classify that list of components. It creates a set, and it iterates through that set and does checks on all of them. Quick note, the value change stump format basically just creates a list of when signals change and what they change to, so we don't have to have a file that stores 10 million clock cycles. It can just list when signals change, which helps with data compression. So the classification algorithm looks for any repetition of values to remove a state-saving component or counter from the list of suspicious ones, and it looks through to see if all values that counter can hold are passed through, and then if it doesn't activate anything, then it's also removed. So this is a very narrow scope for a tool, but as we check out the evaluation, you'll see it is good at detecting taking time bomb Trojans, especially the ones that are designed to evade all other defenses. So the paper itself uses 4 hardware test benches, which use multiple registers. The AES one in particular uses 128-bit registers. In that approach, you'd have to use a lot of clock cycles to iterate through every possibility of value for a 128-bit register. So go back to that definition. What other approach might be useful for eliminating suspicious registers that are very large? The UART module is very similar to the AES one. The RISC-V and OR 1200 are CPUs with their own instruction sets. So linear feedback shift register is a way to randomize the vector input to each of these devices under test. So this is a list of the registers used. You'll see the AES has those 22 128-bit registers, and there's a lot of registers to go through in each of these. So over time, you'll notice that in this graph, the AES test does 75 random encryptions and repeats those exact same 75 random encryptions. Those are 75 random vectors from the linear feedback shift registers that are repeated twice. You'll notice that the amount of constants recognized goes down almost immediately because these are registers that are changing and thus not constant. the number of coalesced and distributed suspicious ones goes down until the 8-bit registers cycle through all 256 of their possible values. Now that they've gone through all their possible values, they're not considered suspicious anymore. But the answer to that question I asked is here. Those 32-bit and 128-bit registers that take a long time to cycle through those values, instead of going through all the millions of clock cycles necessary to eliminate those, the team just repeats the same encryptions, which means they repeat a value. And so those are also eliminated without having to go through every single possible value that they can hold. At the end of this, they found 6 suspicious state-saving components, all of which were injected hardware Trojans that Bomberman was meant to detect. So 0 false positives were found here. Very similar story in UART. It's doing a transmit and receive, and it's doing it twice, alongside some configuration error testing. And then RISC-V uses a simple program that uses all 8 instruction types. This is a program that's given in the RISC-V design repository, the open source repository. This one finds 16 coalesced and 3 distributed systems of counters, and 2 of those 3 distributed ones are suspicious, and 4 of the 16 coalesced ones are suspicious. So there are 13 false positives here, but it's still pretty significant that it eliminated so many. The others that it found suspicious were timeout and performance counters that these instructions didn't utilize fully, constants for CPU features like the hard-coded 0 register or the interrupt mask, and there was one group of these constants that was labeled as well, and that was just the distributed system that was suspicious. Something that I noticed about this test that sets it apart from the others is that there's no repetition. It's just a simple assembly program that uses the 8 basic instructions in order. And I don't know why they didn't repeat it, which probably would have eliminated some of these, but what they did is described in the paper, but they don't describe why they did a basic test like this and not something more complicated designed to utilize all the registers fully, which makes this OR 1200 test also very odd because they do repeat instructions in this one. They do each instruction twice. They use 7 default sets of instructions, and they use one that they designed themselves. It's custom to test the configuration registers. So they added a custom instruction to test those specific registers. So why this is different from the RISC-V one, I'm not exactly sure. It also uses a RISC instruction set, supposedly. So it's running assembly programs, and it finds 9 suspicious state-saving components, 2 of which are distributed, and those are both suspicious, and 4 of the other 7 are suspicious as well. Those were all inserted Trojans. 3 of the 3 false positives were constants. They were shadow registers used for like exceptions specifically for multi-operational arithmetic in a sequence. So it was a very specific use case, but you can tell that this design, if somebody was just testing generally assembly instructions to look for ticking time bomb Trojans, you'd have very few positives to look through and double check that they actually are malicious or not. So the importance of this is that it's not exactly a 100% accurate, but it's a very helpful tool for hardware designers to aid them in their double checking of designs. This is a list of the other existing approaches. I won't go through all of them exactly, but they involved cycling power, finding suspicious combinational logic that doesn't change or has low control values, combinational logic that doesn't contribute to the overall state of the system very much, and just a list of saved suspicious circuitry. And you can see that the only one of these approaches that finds all of the possible ticking time bomb Trojans, including the distributed ones, is Bomberman. And this is a quick overview of their exact hardware tests that they ran on all of these, with all of the exploits they used to avoid being caught by the other approaches. But Bomberman can find this design suspicious, unlike the rest of them. The classification of suspicious state-saving components, it by far dominates the identification stage, and so it defines this time and space complexity. NC basically means there's a data flow graph that has to traverse with n nodes, and there are C simulation clock cycles. So it's n times C. That's the time and space complexity. It's linear. The runtime here is a little misleading because the other approaches here, especially UCI, are general purpose and find a lot of other kinds of Trojans than just ticking time bomb Trojans. So it is nice to see the comparison, but as you can imagine, it would be important to run these other kinds of tests as well to find other suspicious circuitry, not just Bomberman. So, I already kind of mentioned what Bomberman provides for hardware designers, but we'll go into specifics here. This giant graph, is a graph output which highlights in red suspicious state-saving components. Ellipses are combinational signals, or dependent on combinational signals, and rectangles are registers or gated signals. So this is like if you have a design with many registers, instead of having to go through test all of them, you just pull up the graph, you find the 3 red ones, and you go examine those to see if they really are suspicious or just red flags, shadow registers, constants, etc. Most often the false positives they found were a function of just design inputs only, that ended up not changing during the test. This means also that repeating test vectors over and over again, using those LSFRs, the linear feedback shift registers, is a feasible approach. For data path inputs, they just have to repeat the test vector to eliminate the combinational logic that's suspicious. And for control path inputs or gated stuff, they activate the same control path multiple times while also repeating the input data vector. And that is enough to eliminate the suspicious registers mostly. This is a graph of the performance over time, or the number of SSCs found suspicious, and they ran many random vectors through these tests, and you can see that the trend is very similar for all of them, and for UART it's almost identical in every run. So this means that the performance of Bomberman isn't dependent on a specific test case. So latches, as I mentioned at the beginning, can be used as saving state components. You're not really supposed to do that in FPGA design, and if you've ever used an HTL compiler like Hortus, you'll know that it warns you not to do that. But they still have this failsafe in there for sneaky guys, and they have the C++ API can detect latches and will treat them as nodes in the data flow graph as well. Memories, because they are a list of registers, can also be used as part of a ticking time bomb Trojan. The data flow graph is also created for memories by Bomberman, and each block of addressable words is treated as its own saving state component. If there's word alignment mandated by the system, then it will just create one block for each addressable word of memory. But if you can access memory unaligned, as you'll see by this distributed SSC example, you could have a single coalesced component for every word size window of memory. And so basically you have to shift this window over the memory, and each word length window could be its own state saving component. So you have to test all of them. Using the data flow graph, they curb the state explosion, and they create a list of these that are all connected. And so it effectively can also scan memory. You can go backwards from a physical layout that you might think is suspicious from a fabrication firm, and if they provide the IP, which includes the RTL design usually. You can reverse engineer the RTL, or just use the RTL and test it with Bomberman to see if this physical design has any ticking time bomb Trojans as well. So they mentioned that as another helpful use of Bomberman. Because this is a very specific approach, they list other ways that you might use a workaround to this. You can add a new state bit to a counter, which allows the trigger to repeat its counter value, but this actually is just another counter, and so that's a distributed system, and Bomberman will also detect that because of its data flow graph. You could have a certain behavior trigger reset so that a counter doesn't reach its final value, but a triggering of a reset is data-based. That requires like a certain cheat code. It requires knowledge of the test to know what exactly needs to be detected in order to reset, and so that's data-based, and that's not the scope of Bomberman either. Analog trigger Trojans can be implemented at fabrication time, but in design there's no such thing as an analog trigger. So Bomberman, because it's design time, doesn't relate to that either. So in conclusion, this approach to detecting ticking time bomb Trojans is very effective. It's not 100% perfect, but it gets a 1.2% false positive rate. So the amount of circuitry that hardware engineers have to examine for these types of Trojans goes way down with the use of this tool. I'm not exactly sure how much influence this paper has had on the industry. It was released in 2021, so it may not be widely used yet. I haven't heard anything about massive hardware Trojans in the last few years, so either the problem is already pretty well controlled, or we're going to have some bad news down the line pretty soon. And the big takeaway here is that although there are general purpose approaches to detecting suspicious circuitry, the best approach to a specialized complex hardware attack is a specialized complex tool for detecting that attack. Thank you.